Now let's talk about gradient descent in 2 dimensions. So I want to start with a little game. This will be kind of fun. It's a loss minimization game, and go to the following URL. So tinyurl.com/3dloss18. Okay, so I'm going to do that so we can all play along. Okay, and I'll just restart it. All right, so the goal of this game is to move these 3 sliders to minimize the loss. And this red rectangle here, that depicts our loss. All right, so each of these parameters, as we move them, will change the bar, and play along with me. Let's see who can get it first. All right, so as I move parameter 1, we can see it changes the loss, right? And so here the loss is greater when I'm to the right, and if I move it all the way over to the left, it's not quite 0. So we can see that there's a lull point, kind of a low point as we move it. And so if I move it to right about there, it looks like it's the lowest point. I can do the same thing with parameter 2. I can look at this. I move it all the way to the left. The loss is really large. So I'm going to again try to minimize it, and if I move it over here, that looks like it's kind of hard to do this with a trackpad. I recommend using a mouse instead. All right, so there we go, and hopefully this is touch friendly on if you're watching on a mobile device. Okay, now I'm going to try parameter 3. And let's see. Oh, that makes it much larger, and that makes it much larger. So it's somewhere around, oh, there, almost. Oh, so close. Let's try up just a little bit. So let me try adjusting parameter 1 again. Oh, and I got it. Okay. So I won. Hopefully you are able to win also. So this approach where I adjust parameter 1 to try and minimize the loss, and then I adjust parameter 2, and then I adjust parameter 3, and I just keep iterating through that, this is called coordinate descent. And it's similar to gradient descent in that it's another commonly used algorithm that we use to minimize loss. All right. So now let's go back, after a little bit of fun, let's go back to our slides. Okay. So let's change our tip model. So now it has 2 parameters. It's going to have a theta 0 and a theta 1. Theta 0 is our y-intercept, and theta 1 is going to be the slope. All right, so now our tip will be theta 0 plus theta 1 times our bill. And we'll have a new design or feature matrix, which has a bias term, that's the ones here, and it has the total bill. Okay. Now, with this, we can use the same code pretty much that we used for our one-dimensional model. Okay, so first thing I want to look at is a closed form solution. And since this is just a linear model, we can apply the normal equation. So let's go over to our notebook. Okay, so here in the multidimensional model section, we load in our tips data set, and we'll just go through all of this. You can see total bill and bias. Okay, so we have our observations, we have our tips and total bill with bias, we have our tips. And so we want to find the theta hat, the optimal value for theta. And that's going to be a y-intercept of 92 cents and a tip slope of roughly 10 cents, 10.5 cents. Okay. So that's the closed form solution. Our second approach, if you remember from before, was basically brute force. We plot and we look for the minimum point. Okay, and so here is a 2-dimensional plot, and the minimum point on that two-dimensional plot. And it's kind of hard to see because we're taking a three-dimensional surface and showing it to you in just a flat 2D picture. So it's easier to understand this in the notebook. So let's go back to the notebook. Apologies that we're going back and forth in this lecture between the two, but I think it's helpful to be able to see and visualize and actually rotate it. So a whole bunch of commands that we're going to use with Plotly to generate a picture. And here we have the three-dimensional plot where we can see theta 0 and theta 1 and the mean squared error with respect to that. And if I rotate this, now you can begin to see what this surface looks like, right? So we can now see how we can see the minimum point, and you can see it's sort of like a saddle here. And so we see this minimum point right here. Can I actually click on it? There we go, our optimal point. Wait, that's not the same thing we got with our closed form solution, right? Our closed form solution, if we go back up here, was 92 cents as our y-intercept and 10.5 cents as our tip slope. And yet when I look at our minimum here, it's 88 cents for our y-intercept and 11.1 cents for our slope. So why is that? Well, if we actually go and look up here, we can see we're only actually looking at 100 points. And so we're running into the same issue that we had before, which is when you're just uniformly sampling, sometimes your sample point lands on the minimum or very close to it, and sometimes it doesn't. And so that's exactly what happens here. Okay. So that's brute force. The third approach that I want to look at is gradient descent. Okay, so the other alternative, what we'd like to do as an algorithmic approach is we pick a starting point on our loss surface, and then we just follow the slope to the bottom. Now, when we did that in one dimensions, our gradient would tell us move to the left or move to the right. So it was just one direction. But since we're on a 2D surface, the best way to go down is going to be described by a two-dimensional vector. So here we have a waterfall, and this is going to be our 2D surface. And so if we pick a point over here, right, it's going to be a 2D vector that tells us to go this direction. Similarly, if we're over here, it's going to be a 2D vector that tells us to move in this direction, and so on, and so on, and so on. Okay? So again, if we look at our 2D surface, and we pick the star as our initial point, well, the best direction to go is going to be, it looks like something like this white arrow, right? And so that's going to put us at that point, and then we should continue down that slope until we get to the next point. And then from here, which way should we go? Right? Well, looks like we still want to keep going down that surface. But now it looks like we're now on like maybe more of a slant in a different direction, and so we're going to want to follow it down in a different direction. Right? And we'll just keep doing that until we reach the bottom. Okay, so how do we compute the gradient of a two-dimensional function? For a one-dimensional function, we just took the derivative. But for a two-dimensional function, we're going to use partial derivatives, which you saw on the first homework. So if we have the function f of theta 0 and theta 1 equals 8 times theta 0 squared plus 3 theta 0 times theta 1, what is going to be the gradient? Well, the gradient is going to be this function here. The partial derivative of our function with respect to theta 0 times the unit vector I, plus the partial derivative of our function with respect to theta 1 times the unit vector j. Okay? And I and j are just unit vectors in the theta 0 direction and in the theta 1 direction. So I'll start by showing you the partial derivative with respect to theta 0. So it's just simply going to be, with respect to theta 0, we're going to take the power of 2 down, so that'll be 16 times theta 0, and we're going to lose the theta 0 here, so it'll be 3 times theta 1. The question for you is, what is our partial derivative with respect to theta 1? So take a moment, pause the video if you need to, and think about that answer. So, what is it going to be? Well, let's walk through it. It'll be 3 theta 0, right? Because with respect to 8 theta 0 squared, that term's going to drop away, and we're going to lose the theta 1 in the second term. So we'll just end up with 3 theta 0. Now, the way we usually represent this is as an equation like this. So if we write it all out, it'll be 16 theta 0 plus our 3 theta 1 times our unit vector I plus 3 theta 0 times our unit vector j. So again, on a two-dimensional surface, the best way to go down is represented by a two-dimensional vector. And the way we can represent this for an equation is in column vector notation. So our first term, our theta 0 term, is represented by our partial derivative here, 16 theta 0 plus 3 theta 1. And our theta 1 term is represented by our second partial derivative, 3 theta 0. Now, if we have a generic function that has, say, p plus 1 variables, our column vector will just simply be each of those partial derivatives. So the partial derivative with respect to theta 0, theta 1, all the way up to the partial derivative with respect to theta p. Okay, so let's step back a moment. How do we interpret these gradients? Well, think about that loss minimization game that I started with, right? The way you interpret these gradients are, if I nudge the first model weight, what happens to the loss? So again, if we go back here, if I nudge this first weight, what direction is that going to take the loss? And then for the second model weight, if I nudge it, what's going to happen to the loss? And so on and so on, right? And so if I had a vector that was, say, 2, 2, 0, minus 1, right? Well, that would tell me that I need to move in a negative direction for the first, a negative direction for the second, don't touch the third, and then for the fourth, move in a positive direction. Again, it was 2, 2, 0, minus 1, and you move in the opposite direction. So again, this is very similar to what we did when we were playing the loss game. We looked at what happened. If I nudge this weight, what will happen, right? Okay, so batch gradient descent algorithm. We're going to nudge theta in the negative gradient descent direction until theta converges. So our update rule is the next value for theta is going to be the current value for theta minus, we take the gradient with respect, gradient of loss with respect to theta, multiply that by the learning rate, and subtract that from our current value for theta, right? And all our parameters are as we defined them previously. Okay, so we can start by initializing the model weights. And there's always a question, and this is really, for a numerical methods course, but what do you start with your model weights as? And we're just going to start with them as 0, but you could also initialize them to small random numbers, but picking good choices, as we'll see in a moment, is important. But out of the scope of this class. And then we're going to update the model weights using our update rule. So our next value of theta is our current value of theta minus the learning rate times our gradient of the loss with respect to the thetas. So we just repeat this process until the model weights don't change. We reach convergence. Now, at that point, we have our theta hat. We found the value for theta that minimizes our model weights. Okay, so let's have you try this. All right, so we want to derive the gradient descent rule for a linear model with 2 model weights, and we're going to assume mean squared error loss. So let's just look at one observation, so one row of our design matrix, and we have our function is theta 0 times x0 plus theta 1 times x1. And our loss function, our mean squared error, is just going to be y sub I minus x0 times theta 0 times x0 minus theta 1 times x1 all squared. So what is going to be our gradient. So pause the video and see if you can write out what the gradients will be. Here's a hint. Column vector, 2 elements. Okay, so hopefully you were able to write down the solution. But if you weren't, or if you want to check your results, let's go through it. Okay, so we have our loss function is mean squared error, so it's y sub I minus theta 0 times x 0 minus theta 1 times x1 all squared. So our derivative with respect to theta 0 will simply be, we take the 2 down, so it'll be 2 times the quantity y sub I minus theta 0 times x 0 minus theta 1 times x1 times negative x 0. And similarly, our derivative with respect to theta 1 will be the same starting quantity, so 2 times the quantity y sub I minus x 0 times theta 0 minus theta 1 times x1 times negative x1. Right? And so we can write this 2 elements in our column vector. Okay, so the gradient for the entire data set is just going to be the average of the gradients for each point, so we can use our gradient descent algorithm as is. All right, so again, gradient for our entire data set is the average of the gradients for the points, so we can just use NumPy mean to compute that average. All right, so let's go over, again, back to the notebook. Okay, so our gradient, it's a little bit more complicated. Again, it's these partial derivatives. And we can see that with our initial starting point of 0, 0, we end up with minus 135 for our theta 0 gradient and minus 5.99 for our theta 1 gradient. Okay, so that's going to tell us that as a function of our learning rate, we're going to want to move in the 135 direction for theta 0, and we're going to want to move in the 6 direction for theta 1. Okay, and so we have our mean squared error gradient for a single argument, so just as a function of an input theta, we're just hard coding everything in, and we can see that if we just give it a starting theta, which in this case now is a vector, we get the same value as we got before. And so now we can just take that, plug that into our gradient descent algorithm. We're going to use a learning rate of 0.001, and we're going to run it for 20 iterations. And we don't actually get convergence, it looks like. So let's actually try running it for 200 points instead, 200 iterations. Okay. It's a lot of points. It's a lot of points. And we're still not really at convergence. So play around with it. Try playing with the learning rate. Try playing with the starting point. Again, this is really what you would do in a numerical methods course, is how you pick those starting points, how you pick the learning rate to get, and the number of iterations that you're going to want to run in order to get conversion. And so this is why we use numerical optimization libraries, is because they do all of that for us. But I do encourage you to take one of those courses and learn how these things work under the covers. But if you pick all those parameters correctly and run it for long enough, it will converge. Okay, so again, we have our loss function, we have our gradient, and we can just plug that simply into our gradient descent algorithm, and with the right set of parameters, that will give us the correct answer.